So I wanted to start us off slow and then hit a good speed this morning with talking about amplitude interferometry. This is the magic of where you realize that you don't have enough money to build the telescope that you really would like to build, something that's 100, 200, 300, 400 meters in size. And so you use telescopes scattered across the landscape to synthesize that. Now, I want to be, of course, up front with the sorts of things I'm going to be talking about. And be upfront with what a lot of professional astronomers do, which is to, make a lot of assumptions and kind of sweep a lot of things under the rug and kind of cover it up with a kind of a broad sense of smug self-assurance. And so I want to at least own up to that right away. Now, stars are far away. They shine light in all directions, and astronomers aren't really close to stars. In fact, stars are very, very far away. And the light that we see from these stars is effectively parallel. The light has been shining off in all directions, but we're so far away from the stars that light rays that we see from the stars are essentially all in line with each other. And those light rays enter your telescope, and you can actually look inside your telescope and see what's happening for us to try and ease ourselves into the idea of using multiple telescopes at once. The light tends to get focused inside of a telescope. The telescopes like to collect and concentrate light. Now, nobody nowadays uses these nice little refracting telescopes. They use, of course, reflecting telescopes nowadays because big mirrors are hard to come by. Actually, I should maybe not speak so broadly because, of course, there's a lot of refracting telescopes that have been talked about during this particular... Thank you, Bill. Even old refracting telescopes, Bill, but for really big telescopes in excess of a meter, it's hard to use refracting telescopes. So a lot of professional astronomers, when they go to the really big sizes, they go for reflecting telescopes. The biggest reflecting telescope I'll point out was not the 1 meter Yerkes, but it's the 1.25 meter telescope for the Great Paris Exposition. I believe that the exhibition telescope is still, at least the mirror for that, the lens for that telescope is still in a box somewhere in the Paris Observatory. But it's an interesting little thread to trace down. What happens here is you have light that comes to your reflecting element, and mind you, everything that I'm talking about actually does apply for refractive optics, but it's just a little simpler to think about it in terms of reflecting elements. And the light bounces around in a very special way. And what is that special way? Well, you have light that's basically distributed all over the entrance aperture for your telescope, and it's all parallel because we've taken this assumption of light being so far away that all the rays are effectively parallel. And if you actually were to measure the distance that the light travels coming in from every point across your entrance aperture, you actually measure it all the way through off of each surface to the back end to the focal point, measure it very nicely with your ruler right here, you would find that the distance is basically the same to within a tolerance, to within an optical tolerance of about 10 nanometers. And the way a telescope works is by making it so that those distances are all the same. In fact, what happens here is you actually are not just bouncing light around. The light actually, by satisfying that condition, it all shows up at your focal point and it interferes. This is why you don't just get a point of light, you actually get an airy disk for very high magnification. It's an interference phenomenon. All telescopes are interferometers. All telescopes take the light and interfere it in such a way that you get these point spread functions, and that's the reason why they work. In fact, the shape of the telescope, this curve here and this curve here, is a very specific shape, so that that path length condition, that the rays from our star here in red are all the same, that path length condition has to be met by making this a very special shape. In fact, I've put the mathematical formula here for the primary and the secondary. I think this is an RC prescription. There are different shapes that satisfy that condition so that the light rays show up at the back end in such a way that you get the interference and you get the images being made. This shape is also dictated by the fact that not only do you want this to work for most telescopes in the direction in which it is pointing, but you also want it to work off-axis just a little bit, and I've drawn that in here in blue. And so, in fact, with that path length condition working and being able to get the paths all exactly equal for not just one direction, but or an array of directions in the sky, you can actually build up an image. You can actually have your telescope deliver you an image on the sky rather than just a interference along the one axis. Now, astronomers want big telescopes, and so you have to be clever. The problem is that you can be a little too clever sometimes, and so it's always important to remember wisdom from the ages. It is indeed a fine line between clever and stupid. Very fine line, but you know, you can actually deal with that. And so one of the clever things that astronomers have done is decided, well, we can't actually build a primary mirror that's 10 meters in size, so, or 30 meters in size, or 40 meters in size is what astronomers are talking about in places like TMT and ESO and so forth for getting really, really huge telescopes. So what you can do is you can actually chop up your telescope into individual segments. You can actually have individual mirrors that are resting next to each other, and you can actually have them still satisfy this path length condition. You can still have it such that the light that is entering your telescope, bouncing off this prescribed shape, and the secondary mirror comes to the back end and forms an image. In fact, this point spread function, I was very careful. I picked that from a library of Keck point spread functions. You can see it has actually a bit of a hexagonal shape because the outside, out of the plane of the screen here, is hexagonal, so that makes the point spread function a little bit wonky. But it works. It works really well. And the thing is that astronomers should be more clever than this. You can actually take this and, in fact, get rid of a lot of your telescope. You don't even need all that unnecessary glass in the middle of your telescope. As long as you're satisfying the path length condition such that the light across your entrance aperture is coming in, hitting this prescribed shape off the primary and secondary to the back end, as long as those path lengths are all equal, you'll satisfy the interference phenomenon, you'll satisfy the interference criteria, and you'll be able to make an image. And so one of the things you still get when you build a telescope this way is lots of resolution. You still get lots of ability to pick out detail on the things that you're seeing. What you're starting to lose at this point is sensitivity. If you're starting to delete out the glass that's in the middle in your previous telescope here, what you're starting to lose is the ability to catch a lot of light. But if all you're interested in is resolution, if the things you're looking at are bright and you just want a lot of detail on them, then what you can get away with is starting to erase more and more of your mirror. And in fact, a clever thing you can do is, in fact, turn each little piece into its own telescope and have the light come to the back end. As long as you're satisfying this path length condition, more or less, you should be able to get the light to the back end and build the image. Now, one of the things that is a problem is that as you start to do this more and more, the ability to satisfy this path length condition on one axis is good, but as you want to have a field of view, basically satisfy this across a field, this gets harder and harder to do as you put more and more optics into your path. It's hard to satisfy this condition in more than just one direction, but that's okay if everything you're looking at is basically within the point spread function of the telescope. You're actually okay with doing this way. This has been done for a long time already in the radio. This is the Very Large Array that's located in Socorro, New Mexico, and this has been in operation since the mid-'70s, I believe it is. This is easier to do in the radio, and the reason why is with the radio, what you can do is each one of these individual dishes, you can actually not just catch the light, but you can actually detect it here. You can actually throw it onto a detector, and then after the fact, at your leisure, you can actually combine light again. You can detect and then mix the light. In the optical, you can't do that. In the optical, what you really want to do is catch the light and preserve this path length condition that I keep on talking about with these slides, and then mix it back together, and then only then can you detect it. It's not exactly true with other clever techniques that Elliot will talk about later on, but the game has usually been when the optical is you want to mix and then detect. One of the inventors of the laser, who has the Nobel Prize in his drawer to attest to that, is Charlie Towns. He actually does optical interferometry as well. And so we crossed paths at some of these meetings from time to time. And he had a very lucid explanation for this as far as why in the radio you have to detect and mix, and in the optical you have to mix and then detect. His comment was, it's because the value of h bar is what it is. And this tells me a very important truth. This tells me this is why Charlie has the Nobel Prize and I don't. So to crack the resolution problem, what you need to do is be able to put the light together and do so in such a way that you satisfy the path length condition. If you set this up such that you're sending light into the back end, but this telescope's in slightly the wrong spot, or this telescope's in the wrong spot, you actually can correct for this by putting things in your optical path, things we call delay lines, that let you change the amount of path for an individual arm of your interferometer. So if you have one arm over here, you have one arm over here, you can trombone these things in and out and use that to change the path that the light is traveling to the back end. In fact, I think my next slide is a picture. You actually do put mirrors on rails and move these things up and down rails. And this is a picture of two of these so-called delay line carts that are actually in a lab just over on the other island up on the basement of the Keck interferometer. And these are very clever things. You can actually move these particular ones about 10 meters up and down rails. Sorts of devices exist on rails that go out the Char array on Mount Wilson. You actually physically move these carts. There's a motor cart here on the back end, and you have motor cart coupled to the optics cart by means of a voice coil. You have staged servos that allows you to get a lot of range, also get a lot of control in the end, so that you're ultimately moving these delay lines tens of meters with positioning accuracies of about 10 nanometers. This is magic, magic stuff, really. Now, what you want to do is you would like to fix everything in place. I mean, if you have a telescope that's further away from this one telescope, you can think of, well, why do you need these delay lines if things don't move? This is where I had a clever animation showing this telescope actually driving across the landscape, but it doesn't work right now. Sorry. More importantly, though, telescopes, while they can actually move, despite what people might tell you, even if you bolt them into place, what you'll find is that they move anyway, which is to say the Earth is beneath you. And so if you're pointing at a given star right here, your two telescopes might be exactly well spaced to each other relative to the star. But as the Earth rotates, you get to the point where one telescope is closer to the star than the other telescope. And so these delay lines actually have to move in real time to accommodate for the fact that these things don't quite work right, that they don't stay fixed relative to each other. So what does an interferometer see? Well, if you have the two telescopes sending light to the back end and you're not satisfying this path length condition, what you see is basically light from one telescope and another telescope. And on your photometer, it basically doubles up, and that's all you see. But as you get closer to this path length condition, you see, as you basically push this delay line close to the zero path condition, you basically start to see light get bright and dim and bright and dim. It's photometry. It's basically the change in brightness starts to go up and down. When you get to actually zero path between the two telescopes, you get maximum constructive and destructive interference. It's quantum mechanics. It's actually effectively Young's double slit experiment. And you're able to start to see the interference of the light from the two telescopes. This is what it actually looks like. This is not a function generator hooked up to an oscilloscope. This is actually a photometric output from a detector that's being fed by two telescopes at once. And you see the light getting bright and dim as you push through the zero path condition. You also see noise. This is many sweeps of the oscilloscope over short periods of time. But one of the things you want to measure is the contrast. You want to measure how much constructive versus how much destructive interference you're getting relative to some 0 point. And that's the measurement. You actually measure the fringe. A brief tour of what these things look like. This is one of my alma maters where I used to do a lot of work, the Palomar Testbed Interferometer. We had a pair of telescopes here. We could do a different pair of telescopes and a beam combining lab. Unfortunately, PTI no longer exists. This is what Keck is, and Keck was in the basement here. We were going to put multiple telescopes around the site, but that was blocked for non-technical reasons. The 10-meter telescopes make it a very sensitive interferometer. And here is the GSU array that's already been mentioned before. It's kind of hidden in the trees. You have these guys here. VLTI is another place that I've worked. And currently I'm working on the Navy Precision Optical Interferometer. This is what they really look like when you actually think of how an interferometer looks. It's basically a little dicey to get these things to work. Well, so the reason why you do this is that it's silver bullet science. It is a very good analogy in that it is hard to get to work, but it is kind of magic. Every now and then you want to kill a werewolf, such as looking at binary stars. So with a small single star, you get fringes. With a big double star, the fringes squish down. The reason for that is that you can think of light coming from one half of the star, satisfying a path length condition that is different from the other half of the star, and so you have fringes that stack at different places inside your interferometer, and they smear each other out. With binary stars, this is what you see. You actually see a signal from one star and a signal from another star, and so when you stack it, you see this is what you see inside of the interferometer. You can actually think of the case where the binary stars are very close, where the two fringe packets are very close to each other, and then you just get a reduction in the contrast. And so measuring that allows you to actually find out the relative position of the two objects. And so here is this contrast over time. You can basically decompose that into an orbit. And so this is a good orbit. This is 5 milliarc seconds from edge to edge. The error on the semi-major axis is 60 microarc seconds, and allows you to do a pretty good mass measurement on this star. This star is down to, I think, about 1% in the mass measurement. This one's even better, 12 BU, where the error on this orbit is 6 microarc seconds on an orbit that's about 1 milliarc second across. When you combine the physical orbit on the sky, what the orbit looks like, basically, with the radial velocity. Radial velocity is an important component. You can independently, independent of other measures, you can get at the masses and the distance to the object, which is very, very useful. Where you really turn this into astrophysics, though, is then when you basically pull this out and take the masses, you can actually plunk this onto plots now that show evolutionary models of the stars. And particularly with binaries, this is very nice because you have two objects that you can try and pin down. So with this star, you have for one object, you have a particular evolutionary line you want to follow. And for another star, you have a particular evolutionary line you want to follow. In the red is the isochrone. That's the line of basically constant time that you would expect. And you see that the secondary star appears to be a little young off of this isochrone, and the primary star appears to be a little old off of it. So you can see that that's a place where they still maybe need to turn some dials on the model. For stars that are especially hard to model, such as pre-main sequence stars, where the models are really still trying to suss things out, you can actually contribute a lot. So for example, this is a young pre-main sequence star called V773 Town A. Again, you get the orbit from the interferometry, the radial velocity. You can compare it to a variety of these different models that these groups have put together. In particular, here's a zoom in on one of them where the black was the original model of D'Antonio and Matza. I can't pronounce that right. And then an improvement on that where they basically, I think they adjusted mixing length inside the models, produced the blue lines. And the blue, you can see, is definitely an improvement where these lines now basically intersect where the orbit tells you those stars live on this particular HR diagram. And you can see that the models have improved. In the end, I wanted to ease you into interferometry. I'll have another talk in a couple hours that talks more about this, but I wanted to get you started on this idea about how all telescopes are interferometers. They all work by putting light together and interfering light. And optical interferometry, where you use multiple telescopes, is just an extension of that idea. When you do make fringes by interfering the light from two telescopes, you can do this very well with binaries. And you can pull those fringes apart and basically map these orbits on the sky at very low levels, about at the milli arc second and below level. So that's my last slide. Any questions?